Alright, you made it to what's going to be the last page of the notes for chapter 5, just because I don't want to make these videos too long. And I'm going to put the rest of chapter 5 during week 5 of all of this, just so that you have it, but I'm not going to test you on the last part, but I still want to give you that information. So, this is going to be case 3. Now, case 3 is when we have lambda squared minus omega squared is less than 0, which means that the system is underdamped, meaning that our spring is going to go through the equilibrium position quite a few times. It's still going to get back to rest, but means that our spring is underdamped, meaning that the resisting force is not heavily great. Now, because it's less than 0, lambda squared minus omega squared is basically the determinant. So that means that our determinant is negative, meaning that we're going to have imaginary numbers. So we have complex solutions here. So our m sub 1 is just negative lambda plus the square root of omega squared minus lambda squared I, and our m sub 2 is equal to negative lambda minus square root of omega squared minus lambda squared I. Because we have complex solutions, we have our alpha. Our alpha is negative lambda. Our beta is going to be basically the square root of a w squared, omega squared minus lambda squared. And so our position function is just e to the negative lambda t times c sub 1 cosine square root of omega squared minus lambda squared t plus c sub 2 sine of the square root of omega squared minus lambda squared t. So now, here we have an example. A 1 kilogram mass is attached to a spring whose constant is 16 newtons per meter, and the entire system is then submerged in a liquid that imparts a damping force numerically equal to 10 times the instantaneous velocity. Determine the equation of motion if the mass is initially released from rest from a point 1 meter below the equilibrium position. Now, what's nice here is that we have 1 kilogram of mass, and we know that when we are dealing with kilograms, that is going to be our mass. And so we don't have to, do the equation W equals mg, where we can now just say m equals 1, because we are given our mass in terms of kilograms. Now, to find the rest of the values that we need, this equation basically gives us everything. It says is attached to a spring whose constant is 16 newtons per meter. So that means that it gives us that last value in our differential equation. So because it says it's our constant, so our constant is just going to be 16x. So our 16 comes from the fact that it tells us that it's the constant of our spring. And it says that the entire spring is then submerged in a liquid that imparts a damping force numerically equal to 10 times the instantaneous velocity. There's our beta. And so our beta is just 10 because it's 10 times the instantaneous velocity. Instantaneous velocity, that first derivative, times 10. So here is our second order differential equation. We have the second derivative plus beta, and again, our mem is 1, so our beta is 10, and our constant is 16x, and so we can find our lambda and we can find our omega pretty easily. So our lambda comes from the fact that 10 should equal to 2 pi. And because 10 is equal to 2 pi, we can find lambda fairly quickly. Let's divide both sides by 2, so our lambda is going to be 5. Our omega is 16 is equal to omega squared, square root 16, so our omega is going to be 4. So when I substitute in to see what type of case I have I have 5 squared minus 4 squared, which is going to be 9, which is greater than 0, so I'm dealing with case 1. Now, our x sub 0 equals 1, or x prime of 0 equals 0 comes from the fact that determine the equation of motion if the mass is initially released from rest from a point. So we're released from rest from a point 1 meter below the equilibrium position. So our initial position is 1 meter below the equilibrium position. So since we're below, it's positive 1, and because we're releasing it from rest, our initial velocity is 0. So to find our equation of motion, our position function, what we're going to do is now just going to substitute in everything into case 1, which we're told that our x of t is equal to e to the lambda t, or negative lambda t, times c sub 1 e to the positive square root of lambda squared minus w squared plus c times c plus c sub 2 e to the negative square root of lambda squared minus w squared. Now, because that's 9, the square root of 9 is 3, that's why it's positive 3 and negative 3t. And now what we want to do is we want to solve for c sub 1, c sub 2. So what I'm going to do is I'm just going to go ahead and distribute in my e to the negative 5t into the parentheses, so it makes it a little bit easier. So I just have c sub 1 is equal to e to negative 2t plus c sub 2 times e to negative 8t. Now, to find our c sub 1, c sub 2, we're going to use the fact that our initial position is 1. So I'll plug it in. 1 is equal to c sub 1 e to the 0 plus c sub 2 e to the 0, because t is 0. So basically, 1 is equal to c sub 1 plus c sub 2. To find, so then we're going to use our initial velocity, which is going to be x prime of 0 is equal to 0. So here I'm going from right here. We take the derivative. This is what we get for the derivative: negative 2 c sub 1 e to negative 2t minus 8 c sub 2 e to negative 8t. Plug in 0 for both our t and our instant our velocity, our initial velocity. And when we plug in 0, we're going to get 0 is equal to negative 2c sub 1 minus 8c sub 2. Now what I'm going to do is I'm going to add both of these together, but I'm going to multiply this by 2 to get rid of c sub 1. So here I multiplied that first equation by 2, and I'm adding it to the second equation to solve for c sub 2. When I do that, I get 2 is equal to negative 6 c sub 2. Divide both sides by negative 6. So my c sub 2 is equal to negative 1/3. And then when I plug this in into, I would just plug it into this part right here. C sub 1 is going to equal 4/3. So there's my equation of motion, my position function, which is x of t is equal to 4/3 e to negative 2t minus 1/3 e to the negative 8t. All right, now for the last example we're going to do is example 4. After a mass weighing 10 pounds is attached to a 5-foot spring, the spring measures 7 feet. This mass is removed and replaced with another mass that weighs 8 pounds. The entire system is placed in a medium that offers a damping force that is numerically equal to the instantaneous velocity. So the first thing we're going to do is we want to find the equation of motion if the mass is initially released from a point 1/2 foot below the equilibrium position with a downward velocity of 1 foot per second. So the first thing that, of course, we want to do is we want to find mass. Now, everything is given in terms of weights. We're dealing with 10 pounds and 8 pounds. What we're going to use is 8 pounds because this is, the 10 pound was removed and replaced with the 8 pound weight. So therefore, we're going to use 8 pounds. So 8 is equal to m times 32. 32 again is used because we're talking about feet. So therefore, our mass is going to be 1/4. Now to find our K, we're going to need to use the 10 pounds. The reason why we have to use the 10 pounds is not the 8 pounds is because we know the pull of the spring. We know the S. it was 5. When we attached the 10-pound weight, it became 7. So that pull was 2 feet. And I'm able to solve for my K there. And I can use this for my equation because it's going to have the same effect given, the 8 pounds, how, much it's going to come down. So, because I don't have any measurement for the pull for 8, I'm going to find my constant K using the information that I do have. So 10 is equal to K times 2, again using Hooke's law. And so we're able to find that K is equal to 5. Now, our beta is equal to 1 in this case. And why the beta is equal to 1 is because it says that the entire system is placed in a medium that offers a damping force that is numerically equal to the instantaneous velocity. Because it's numerically equal to the instantaneous velocity, it's just 1. So when we plug into our second order differential equation, our mass is 1/4 x double prime plus 1 times x prime. Our that beta coming from this fact that it's equal to the instantaneous velocity, and the fact that our K is 5, so plus 5x equals 0. So now, and then our initial position is 1/2 because it's 1 foot below, so it's positive, and our initial velocity is going to be 1 because it has a downward velocity of 1 foot per second. So now, in order to find our lambdas and our omegas, we want to have our leading coefficient to be 1. So we're going to divide everything by 1/4, and we get 4x prime plus 20x. So that means that our 2 lambda is equal to 4, so our lambda is 2, and our omega squared is equal to 20. And really, we only need the omega squared right now because of what we're dealing with. So our omega squared is equal to 20. We could find the omega, 2 squared root of 5, but all we really need is that omega squared. So now that we have our lambda and our omega squared, we know that it's a second order differential equation with an instantaneous velocity. So we're going to find out what case this is. When I do lambda squared minus omega squared, I realize that it's 4 minus 20, which is negative 16, so it's less than 0, so we're dealing with case 3. Because we're dealing with case 3, it's just going to be our equation of motion is just e to the negative lambda t, so e to negative 2t times c sub 1 cosine of the square root of omega squared minus lambda squared t. Well, if omega squared minus lambda squared is, if lambda squared minus omega squared is negative 16, if we do the opposite of omega squared minus lambda squared, we get 16. The square root of 16 is 4, so that's why we have 4t for both of those. So now we are going to plug in our x sub 0 equals 1/2 when our initial position is 1/2, so 1/2 is equal to, all of our t's are 0. That means that's just e to the 0 is just 1. Cosine of 0 is just 1. Sine of 0 is 0. So we just have c sub 1. So our c sub 1 is 1/2. To help us find our c sub 2, we're going to take the derivative of x of t, or the equation of motion. When we do that, we get negative 2e to negative 2t times c sub 1 cosine of 4t plus c sub 2 sine of 4t plus e to negative 2t minus 4c sub 1 sine of 4t plus 4c sub 2 cosine of 4t. What we want to do now is plug in our initial velocity, so 1 is equal to, and all of our t's are 0. If we do that, we're going to end up with negative 2c sub 1 plus 4c sub 2. Our c sub 1 we know is 1/2, so that's negative 1. Add that to 1, so 1 plus 1 is 2. Divide that by 4, so c sub 2 equals 1/2. So our equation of motion is x of t is equal to negative 2t times 1/2 cosine of 4t plus 1/2 sine of 4t. Now, the next step is to express this in the form of a sine of just sine, really. And so in order to do that, it's basically the same thing we did in our last section, where our amplitude is going to be found by squaring our constant c sub 1 and c sub 2. And when we do that, our amplitude is going to be 1 over the square root of 2. Again, you can express that as square root of 2 over 2. Our phi is going to be also the same thing. Tangent of phi is equal to c sub 1 over c sub 2 because we're converting this into sine, which we get 1. So phi is going to be the inverse tangent of 1, which is pi over 4. And we're in the first quadrant because both values are 1, so it's pi over 4. Now, to expression in terms of sine, part of our term in front of sine, we're going to keep that e to the negative 2t. So that's the only thing that's going to be different. It's just that you keep that leading term e to the negative 2t in front. So here's our amplitude, here's our omega t, and here's our phi. This is kept from the fact that we're multiplying both our sine and cosine by e to negative 2t. So that's going to stay there. And so now we have our equation in motion in terms of just one trig function, and that is instead of two trigs, and that is just by sine. Now, the last part says find the times at which the mass passes through the equilibrium position heading downward. So to find this heading downward, what we want to do is we want to see where our position is equal to 0. And so basically what we're going to do in order to see where this is equal to 0, since we're dealing with sine and e to negative 2t is never going to be 0, this is going to go away. The only time that sine is equal to 0 is pi, 2 pi, 3 pi. So we're going to set the 4t plus pi over 4 equal to pi, 2 pi, 3 pi. So we're just going to start saying it equal to pi. If we do that, then we subtract pi over 4. We're going to get 3 pi. We subtract the pi over 4. And then solve. And then we're going to divide by 4. And so here we're left with a 3 pi over 16. Now, we can't use the 3 pi over 16 because that's not going downward. That would be going upward. So then we have to use our next part because just the way that we're moving. Because if we're talking about, using pi, 2 pi, 3 pi, and we're talking about sine, when we're talking about sine, we're talking about the y values. And so therefore what we want is all the times where it's going to be coming into the negative. So we're going to be wanting the 2 pi and the 3 pi. And because of that, we're going to be left with, if we do the math here, 7 pi over 16. And then we want to find the next time 7 pi over 16. So because we have pi over 4, every phase is going to be done by 8, so that's why it's 8n. So t is equal to 7 plus 8n times pi over 16. And this will give us our 2 pi. The next one will give us our 4 pi, our 6 pi, our 8 pi. And the reason why we want all those evens is because we want it when the position is heading downward. And that's it. Please let me know if you have any other questions on this. Again, we're